Welcome to the GoEngineer YouTube channel. My name is Paul Nishihira, and for part 1 of this two-part video tutorial, we are going to take a detailed look at the fundamentals of two-axis turning and how easy it is to create, simulate, and generate NC code using the functionality of automatic feature recognition within SOLIDWORKS CAM Professional and CAMWorks. So let's get started. Here at GoEngineer, our number one priority is to ensure customer success from the products and services we offer. A wide range of training opportunities from our certified instructors allows you the flexibility of what topic meets your needs and your schedule. We also offer comprehensive resources that is free to everyone and well established from many years of our technical experience. If you would like to find out more, feel free to contact us and we'll be more than happy to help out. Although this tutorial is primarily for individuals new to two-axis turning, the detailed information presented will benefit all skill levels. For those seeking advanced turning functionality, it won't be covered here as this is available in other CAMWorks packages. However, feel free to contact us directly if you would like to find out more information. This tutorial applies to anyone using SOLIDWORKS, along with a license of SOLIDWORKS CAM Professional and/or CAMWorks, using out-of-the-box default settings. What this means is there are no customization settings applied to the technology database or CAM-specific system options, or as I like to refer to, no demo magic. Instead, it will be solid, time-tested best practices sprinkled with many SOLIDWORKS and CAM-specific tips and tricks. Simply put, we are going to generate NC code from a part file. Let's take a look at what's involved. Obviously, we need a part model to begin with, and ideally, this would be a SOLIDWORKS part. But any other CAD neutral formats such as Parasolid, STEP, or IGES are acceptable as well. For those of you who want to follow along interactively, I got you covered with a detailed drawing before we switch over to our SOLIDWORKS environment. Define our CAM-specific machine environment, which identifies what type of machining center is to be actively used for machining our part model. Define our stock, which is the material type, size, and shape from which the part will be machined from. Review the CAM-specific system options, and as an added bonus, SOLIDWORKS system options. Create a setup. Using automatic feature recognition by clicking on the Extract Machinable Features command button. Generate that information into operation plans. This contains how each machinable feature is to be machined and how the NC code will output. And from the operation plans, we'll generate toolpath to see how the cutting tool is used for that operation. Next, we will review our work by using the available verification tools, such as Step Through Toolpath and Simulate Toolpath. And finally, post-process and review the NC code. For those of you who are unfamiliar with two-axis turning or parts frantically spinning sideways, I'd like to take a moment to discuss the importance of understanding the following information that's related to this picture. Safety being number one is a given, but I also want to minimize any frustrations using SOLIDWORKS CAM Professional and CAMWorks. The left side of this picture shows the main spindle and the chuck fixture, which is holding the round stock. This is known as a rear turret or single turret machine configuration. To the right of the chuck fixture is the round stock, also known as our part or workpiece. It is critical that the spindle center line be set properly in the software in order for feature recognition to automatically recognize features for machinability. Generally speaking, and following the right-hand rule, the X, Z, and Y-axis markers represent the main spindle coordinate system. In this example, the main spindle coordinate system is located from the front face of the part and along the spindle axis center line. However, this location can be adjusted to a different position. Alternate locations, such as the center of the part, or even the back face of the part and/or stock, are all valid choices. The Z-axis arrowhead points in the Z positive direction, or away from the front face of this part, and along the part's spindle centerline or axis. The X-axis arrowhead points in the X positive direction as shown. Machinable features are based on the part's geometry, which is the shape of a feature, as well as its topology, or how the features are related to each other. This is the main benefit of using SOLIDWORKS CAM Professional and CAMWorks feature-based machining technology. Supported turn feature types include base feature, outside diameter profile feature, inside diameter profile feature, groove feature with vertical walls, and cutoff feature. And yes, threads, internal and/or external, are supported as well. But consider using cosmetic threads and/or hole wizard features in lieu of actual thread features themselves. As mentioned earlier, this part will be used to generate NC code. Feel free to pause the tutorial and replicate its design using SOLIDWORKS best practices. When designing a part for manufacturing, location of the SOLIDWORKS origin, as shown in blue, is always a consideration for ease of setup in the CAM environment. When looking at this part in an isometric view, the SOLIDWORKS origin is established from the right face and center of the part. One thing to keep in mind is that if the part is created or imported in an odd fashion, and let's be honest here because it's happened to everybody, SOLIDWORKS CAM and CAMWorks doesn't care because we will be establishing our own SOLIDWORKS coordinate system, which properly orientates how the part sits within your machining center. Although this part uses various types of SOLIDWORKS features, I want to review them individually using the rollback bar as they all complement machinable features in the CAM environment. The first feature consists of a simple circular sketch coincident to the SOLIDWORKS origin and using a blind end condition to establish its boss extrude feature. The second feature is more involved from its parent sketch. In addition to traditional horizontal and vertical entities, I've also created a sketch chamfer. Tip number 1, if you want to exit Sketch but don't feel like moving your mouse to the extremes of the SOLIDWORKS user interface, press the D key, D as in Delta, on the keyboard. This will display the sketch confirmation dialog wherever your mouse is currently at. This cut revolve feature will remove part geometry which satisfies a rectangular groove machinable feature. Tip number 2, takes advantage of the SOLIDWORKS efficiency tool called mouse gesture, or as I'd like to refer to as the Wheel of Fortune. Simply right mouse click, hold, and move the mouse ever so slightly to display your current commands. This SOLIDWORKS function is totally customizable, and I'll share a link below in the description field for those who want to take advantage of this. Hole Wizard is the next feature, and it's a great way of not only capturing SOLIDWORKS design intent, but also a great way of leveraging this information as a machinable feature in the CAM environment. Tip number 3. For those who want to toggle quickly between orthogonal views, press the space bar and the View Orientation dialog box displays wherever your mouse is currently at. Our next item is known as an applied feature, that is, no sketches are required. Simply click on this fillet feature and it displays its location with radius value in the SOLIDWORKS display area. For our final applied feature, I have a chamfer located at the nose of this part. As with the fillet feature, simply click on it to display its location and appropriate values in the SOLIDWORKS display area. One last tip here within the Feature Manager design tree. If you want to do some housekeeping and hide exposed sketches from its associated features, right mouse click anywhere within the Feature Manager design tree, then left mouse click on Collapse Items. One feature required to properly establish the CAM environment is the use of a fixture coordinate system, as this defines the home point or main zero position of the machining center. This assignment is mandatory, as it properly orientates the defined machining center on how it approaches and machines the part. On the front face of this part, let's create a new sketch. If you want to take advantage of the Customize shortcut menu, tip number 4 has got you covered by pressing the S key, or S as in Sierra. From the SOLIDWORKS origin or center of this part, create a vertical line and add the appropriate sketch relations to fully define it. This line will be used to help orientate our fixture coordinate system. Exit sketch. To help visualize the orientation of the fixture coordinate system, switch the model orientation to isometric view. Then press the S key one more time for commands available at the feature level. From the cascading menu, select Coordinate System. Inside of the Property Manager, we are only concerned with 3 selections: the center point or SOLIDWORKS origin of our part, the gray vertical line which establishes the x-axis, and finally an entity, whether it is a planar phase or a reference plane that establishes the normal to direction for the z-axis. Axis colors, green, red, and blue, help determine proper orientation, and it is the same colors used for the SOLIDWORKS reference triad. Toggle the reverse direction icons to achieve the desired result as shown in the SOLIDWORKS display area. Once done, press the D key on the keyboard or the green check mark, as this will display the Property Manager confirmation dialog wherever your mouse is currently at. Depending on your current visibility settings, you may or may not be able to see your newly created fixture coordinate system. To adjust this, expand the Heads-Up View Display menu and click on the View Coordinate Systems icon, as this will display the fixture coordinate system that we had just created. An enhancement for SOLIDWORKS 2022, a cool tip to quickly display available reference planes and the fixture coordinate system, simply press on the Q key on the keyboard. When done viewing these entities, left-click anywhere within the blank SOLIDWORKS display area. When switching over to the CAM environment, it seems to be somewhat overwhelming, but in all honesty, they are logically displayed for the methodical workflow for which we are about to do. The CW tab, or CAMWorks feature tree, is where we are starting. For people using SOLIDWORKS CAM Professional, the icon highlighted in red will be displayed. As with SOLIDWORKS, we have several tabs displayed from the CAM Command Manager. The various command icons are displayed so that you are working from left to right or top to bottom to properly set up the CAM environment. Additionally, when hovering over a specific command function, a tooltip is displayed which helps in determining what needs to be done. Defining the machine environment is accomplished by clicking on the Define Machine icon up in the Command Manager. Another method that I personally use is to right-click on the machine node, then left-click on Edit Definition. This page displays several tabs which helps determine what machining center is used: cutting tool cribs, post-processor assignment, and coordinate system assignment. Working methodically from left to right, we'll start with the Machine tab. For those of you using SOLIDWORKS CAM Professional, there are slight differences in available selections, but overall, for what is needed for this tutorial, we will be selecting Turn Single Turret, Inch under Turn Machines. Once this selection is made, notice how the machine environment changes on the CAM feature tree as it now complements turn machining. On the Tool Crib tab, we will be selecting Default Tool Crib 2 Rear Inch as the active set of cutting tools to be used for machining. A detailed description of these tools is listed in the upper field of this page. The Post Processor tab will display all available default post processors, and its main job is to parse our CAM information into NC code output. This NC code is then used to control operations of the CNC lathe. Although we have many choices, for this tutorial, we will be using the Haas ST20. Once highlighted, again, click on the Select button as this selection assigns it as the active post processor from the available file location listing. The Posting tab displays any existing logic from the selected post processor. We can type in 100 as our program number, determine its Z and X preset values, which determines machine home position, as well as maximum spindle RPM. Now, putting on my sales hat, GoEngineer offers custom post processor services which complements your machining center and desired NC code output based upon your needs. As with SOLIDWORKS mouse gesture customization, I'll include a link below in the description field for those who are interested. The Setup tab in 2-axis turning allows us to define a new user-defined coordinate system and assigns it as the fixture coordinate system for the main spindle. Since we previously created a SOLIDWORKS coordinate system, I'm going to specify this under the Method field and choose it from the available Coordinate Systems field or from the SOLIDWORKS Flyout Feature Manager tree. The SOLIDWORKS display area will update based on the selections made, and select the green check mark to accept these settings. For those of you who want to use a dedicated work coordinate value, it's a matter of selecting the proper radial button and assign a number accordingly. For this tutorial, let's go ahead and use work coordinate G54. Other settings below, such as spindle direction, turn feature section plane, and turn feature display pane, can be adjusted. For this application, we'll leave these settings as is. Although we are achieving the same results, another method of creating a new SOLIDWORKS coordinate system and optionally assigning it as the fixture coordinate system for the main spindle can be done by the following method. Inside the main spindle coordinate system property manager, I'm going to select User Defined. This updates the field selections so that an entity, part vertex, or stock vertex can be selected in the SOLIDWORKS display area. After selection, it's just a matter of orientating the X and Z axis to its proper alignment. Once conditions are satisfied, the Create SOLIDWORKS Coordinate System icon becomes active. Then it's a matter of giving it a meaningful name and assigning it as the active coordinate system. After clicking on OK, the main spindle coordinate system property manager updates with its new assignment. If you notice in the SOLIDWORKS Flyout Feature Manager tree, we now have a new SOLIDWORKS coordinate system. Whichever method you choose is up to you, but to reiterate, an assignment of a SOLIDWORKS coordinate system for the main spindle is important in 2-axis turning. As this was showing you an example of a different workflow, I'm going to reselect our original SOLIDWORKS coordinate system, which places its location from the front of the part. The last tab we'll cover is Chuck and Fixture. Appropriately named, we can determine its shape from various sources. In keeping with the theme of out-of-the-box settings, I'll go ahead and use a standard shape, and from the available chuck selections, you can see the chuck preview display and its relationship to our part. The technology database offers a wide selection of chuck fixtures to choose from. For this tutorial, let's use the 4-inch 2-step chuck available from the pull-down menu. Meaningful comments such as vendor information or specific notes can be created. Numeric value changes to chuck parameters, outside diameter, inside diameter, and thickness, and jaw parameter settings such as orientation, number of steps, etc. not only update the preview window, but it also updates the SOLIDWORKS display area. Let's keep these current settings and select the green check mark for OK. As with any SOLIDWORKS model display, we can choose what type of display is shown from the pull-down menu for our chuck and fixture. For this application, let's choose transparent. Select OK to confirm our settings and exit the Define Machine page. Another method of chuck and fixture display is to right-click on the machine node, hover over Chuck and Fixture Display, then choose its display style, and when to have it shown by hovering over the machine, setup and/or operation nodes. The stock manager in 2-axis turning environment is the material from which the part will be machined from. By right-clicking on the stock manager node and left-clicking on Edit Definition, the property manager contains settings that defines the stock. The CAM-specific materials are used for feed and speed calculations and uses a different database, which is defined from the technology database and not from the SOLIDWORKS materials library. Let's use the material grade 316 stainless steel. Various stock profiles, such as the default round bar stock from a revolved sketch, CAM-specific work in process or WIP, an STL file, or even a solid part file can be used. Choices between solid and chord can be used to help simplify machining. When using the default round bar stock, it is the smallest cylinder or bar stock that the part will fit into. Since we want full cleanup of all outside diameter features, I'll adjust my values to the next common size of 2 inches. Another tip that I find is helpful is using the Tab key to toggle between different fields in SOLIDWORKS CAM and CAMWorks. If you were to execute the Enter key, not only will it accept its current settings on that page, but it'll also exit you out of the current command function. Once the outside diameter is established, tab down to the front face of the stock offset and key in the value of 50 thousandths, as this will establish a face machinable feature. The initial value of 1 inch will be the distance between the back face of the part to the back face of the stock, as well as help determine if we have enough clearance to the chuck and fixture jaws. To get a better idea of locations for all entities, let's look normal to the front view, then select OK to confirm our settings. When you select the machine node and then hover over the stock manager node, you can see those items in preview within the SOLIDWORKS display area. It's obvious that we have clearance issues, so let's edit the definition for the stock manager and increase the back face of the stock offset to 1.50, as this will give us enough real estate not only for the chuck and fixture jaw clearance, but also for the cutoff tool and its holder. This section of the tutorial covers personal preferences within the SOLIDWORKS and CAM-specific user interfaces. If you want to adjust the color vibrancy pre-2016 SOLIDWORKS, feel free to follow along to these adjustments within the SOLIDWORKS system options, or click on the gear wheel icon at the top. Under the System Options tab and Colors subpage, expand the icon color pull-down menu and choose Classic. Select OK to accept this setting. You will now notice that the SOLIDWORKS command icon colors have changed not only in the Command Manager, but also in the SOLIDWORKS Feature Manager design tree. Color vibrancy is adjustable within the CAM-specific system options, and it will give us an opportunity to explore other settings. From the Tools pull-down menu, select CAMWorks or SOLIDWORKS CAM, then Options. For those of you who don't save work frequently or sometimes forget, mark the checkbox Auto Save Every ... and adjust the time frequency to your preference. Keep in mind that its default value is 1 minute, which is annoying when you're in the groove of programming toolpath and having the autosave function break your rhythm. I'll leave this choice up to you. On the Turn Feature tab, Revolve section from the pull-down menu is the preferred method for our part when extracting machinable features. Turn features are recognized based only on the spindle axis. Any faces on the part that are not concentric about the spindle axis are ignored, and any user-defined turn feature section plane is ignored. Plane section would normally be used if the part contains protrusions or ears on the outside diameter of the part. As the name suggests, the Display tab controls visual properties of the CAM user interface. These are my personal preferences, so feel free to checkmark the box for Display 3D Origin Marker, select Classic for the icon colors, and after doing so, the notification message indicates that you will need to exit SOLIDWORKS and then restart SOLIDWORKS for these changes to take effect, and I'll do this here shortly. The work coordinate system icon is impossible to see at its default value of 1, so I'll change this to 2.5. And finally, I'll change the toolpath line weight to a value of 2. Any changes done on the Simulation tab affects the graphical display for Simulate Toolpath. For now, no changes will be made here. The Update tab contains many options that modify the rebuild functionality in CAMWorks and SOLIDWORKS CAM. While these default settings are important, verify that the checkmark options under Prompt to Rebuild are selected. This will save you time from manually rebuilding your part and CAM data if any changes are made. And finally, the File Locations tab contains all active file locations unique to the CAM-specific environment. Out of all these settings, checkmark the box Open G-code file in CAMWorks NC Editor, as this will allow you to review and edit your NC code in this application, unless you're old school and like using Notepad. Select OK to confirm these settings. At this point in time, I'll save my existing part file, then close SOLIDWORKS as I want to update my CAM user interface with the new display settings. I'm sure everyone here has seen SOLIDWORKS on startup, along with the add-in programs of SOLIDWORKS CAM or CAMWorks. I'll fast forward through this process so we can see the new display changes to the CAM-specific user interface. You'll notice that the CAM-specific Manager tabs now display different colors. Additionally, various icons on the CAM-specific Command Manager will also display these same colors. All of it is similar to the display changes of the SOLIDWORKS user interface. Alright, the next step is to run Extract Machinable Features by clicking on the icon located on the CAM Command Manager, or by right-clicking on the top-level CAMWorks or SOLIDWORKS CAM NC Manager from the cascading menu. Automatic feature recognition analyzes the part model, creates a turn setup, and identifies turn machinable features. As shown earlier in this tutorial, machinable features are recognized based on the part's geometry, or the shape of a feature, and its topology, or how these features are related to each other. After some flashing and dashing, we now have a single turn setup and its machinable features underneath in blue. All this information is created when we define the stock as a round bar stock, and it will be machined using tool orientations that are relevant for a rear turret machine configuration. The blue color indicates we don't have any operation plans generated yet. One thing you'll notice in the SOLIDWORKS display area is the larger work coordinate system icon. Much easier to see in my opinion. Another tip that I like to use is to orientate my part so it's relative to the machine view. Right-click on Turn Setup 1, and from the cascading menu locate Set View. Then left-click on Turn ZX. This will display the part normal to Turn Setup 1 machine view. Keep in mind these views may be different from your SOLIDWORKS orientation views as invoked by the spacebar. As you click on each machinable feature, you'll see its profile highlighted in the SOLIDWORKS display area, as this is an easy way to determine where it's located on the part. The next step is to generate operation plan, which contains information on how each machinable feature is to be machined and how the NC code will output. As with Extract Machinable Features, the command icons are located in similar fashion. After more flashing and dashing, the CAM operation tree is now active, along with our single turn setup and the relevant operation plans from its machinable features underneath in blue. To actively view, or if needed, edit definition of our toolpath, we need to generate toolpath, as this will convert all of our operation plans from blue to black text colors. Once this process is done, you can hover over each active operation plan to see its corresponding toolpath in the SOLIDWORKS display area. Yellow warning markers indicate that the cutting tool for this operation plan was not available from the selected tool crib. To satisfy the operation plan's requirements, it is used from the main tool library of the technology database. Clear this warning. Simply right-click on the operation plan with the warning marker, navigate to What's Wrong, then select Clear to acknowledge this warning. We'll do the same process for the other operation plans below. The toolpath verification process can be done two different ways. The first method is known as step-through toolpath. This function can be used to see all toolpaths from the CAMWorks or SOLIDWORKS CAM NC Manager, the turn setup itself, or each individual operation plan. For this tutorial, simply right-click on Turn Setup 1 and left-click Step Through Toolpath. The Step Through Toolpath Property Manager allows you to step and play forward or backwards, fast forward or backwards, filter its position based on next toolpath, operation, and tool. Controlling speed and manually positioning its step-through location is controlled by these nifty slider bars. Various display settings for tool and holder can be turned on or off. Important information such as machine home location, tool position, tool name and description, feed rate, and RPM are listed towards the bottom. You will also notice in the SOLIDWORKS display area that our work coordinate system G54 is actively displayed as well. Once done viewing, select the green check mark to exit this property manager. Similar to step-through toolpath, the settings and parameters for simulate toolpath allows you to view a graphical representation of material removal for the verification of the machining operations. You can step and play forward or backwards, fast forward or backwards, filter its position based on next toolpath, operation, and tool. Controlling speed is adjusted by this nifty slider bar. You will also notice in the SOLIDWORKS display area that our work coordinate system marker is actively displayed. Various display settings for part and stock comparison, section view, stock, tool, its holder, chuck fixture, and target part can be turned on or off. Under Options, controls for displaying collision detection between the tool and its holder are independently adjustable. For those wanting to take advantage of Work in Process Stock, or WIP, this is where the display image is saved once completing Simulate Toolpath. Now, let's go ahead and run it. To show differences between the assigned stock and our part, click on Show Difference. Unique colors and a reference chart is shown in the SOLIDWORKS display area. Any colors in blue indicates presence of stock material. The color green indicates the part is machined to net size, and any of the warm colors, yellow through red, means that overcutting is done on the part. Since our part has an ID feature, click on Section View, and from the pull-down menu, select 3/4. This cool function allows us to view any internal features of our part without resorting to the traditional SOLIDWORKS section view tool. When we show differences between the stock and our part, you can see that the drill operation did not entirely penetrate, leaving the excess material from the drill point to the shoulder. Let's go ahead and fix this by exiting out of Simulate Toolpath, and we'll edit the definition for the drill operation plan. The operation parameters page is now displayed with the tool tab selected. You can visually see how the cutting tool is positioned based upon your mouse cursor location in the SOLIDWORKS display area. Obviously, we need to adjust our depth. Overriding the default depth value is done on the Feature Options tab. Another tip here, after making any changes within the operation parameters, click on the Preview button at the bottom, as this will update based upon any changes just made. The drill tip went deeper, but not enough to machine a clean through hole. Expand the operation parameters once again, select the Override Machining Depth icon, and key in the value of 1.15. and select Preview to update. We now have a visual confirmation of machining a clean through hole. Expand the operation parameters once again. Select OK to confirm these changes. Now, it's a matter of running Simulate Toolpath once again. Click on Show Differences, click on Section View, and from the pull-down menu, select 3/4 one last time and rotate the part as to visually confirm that we did indeed machine a through hole. Select OK once done viewing. We're actually almost done, as post-processing is our final step of this tutorial. Since we want to post-process NC code for all operations, right-click on Turn Setup 1, then left-click on Post-Process. Let's give the file a meaningful name and path location. You can also specify the file extension type so it's compatible with your machine controller. The Property Manager for post-process allows us to step, play, or fast forward the parsing of our generated toolpaths into NC code. This NC code will be available for review and editing using the CAMWorks or SOLIDWORKS CAM NC editor, and it is using the Haas ST20 post-processor. Select the green checkmark for OK to complete this function. And here's our NC code. As you highlight each line, we can see various information that's going to be used when this NC program is loaded into our CNC lathe. Now, the caveat here is that you need to review this NC code and perform edit changes so it is safely compatible for your individual application. So let's take a quick review at the entire workflow of generating NC code using SOLIDWORKS CAM Professional and CAMWorks Automatic Feature Recognition. First is the importance, placement, and usage of a mandatory SOLIDWORKS coordinate system. Next, define the parameters of the machine environment, especially the assignment of the main spindle coordinate system. Specify the material type, shape, and size within the stock manager. A high-level overview of CAM-specific and SOLIDWORKS system options. using automatic feature recognition by clicking on the Extract Machinable Features command button. Generate operation plans from valid machinable features. Then generate toolpath to see how each cutting tool is used for that specific operation. We will check our toolpath by using Step Through Toolpath and Simulate Toolpath. And finally, post-process, review, and if necessary, edit our NZ code. And that is a detailed look at how easy it is using automatic feature recognition with SOLIDWORKS CAM Professional and CAMWorks 2-axis turning. If you enjoyed this tutorial, please subscribe and leave us a comment below if you have any suggestions that you'd like to see in a future video. Visit our website, goengineer.com, for access to professional training, upcoming events, and more from your #1 online technical resource. This is Paul with GoEngineer. Thanks for watching.